So in this video we're gonna look about the ideal solution, non-ideal solution and azeotropes. So if we try to distinguish between ideal solution and the non-ideal solution, then if we talk about the ideal solution, what we call the ideal solution. So ideal solution is which obeys the Raoult's law. So ideal solution is like which obeys the Raoult's law, and non-ideal solution is which do not obey the Raoult's law. So non-ideal solution is divided into two parts: shows positive deviation from Raoult's law, show negative deviation from Raoult's law. So when it forms the ideal solution, so delta mixing of V, that is equals to 0, or delta mixing of H, that is equals to 0, means there will be no release in heat, no change in volume. And when we talk about intermolecular attraction force, so the attraction force that is between A and A, that is approximately equals to, that is force between me and me, and that is also approximately equals to force between A and me. So when we talk about the shows positive deviation, so in that case delta V mixing is greater than 0, and which here delta H mixing is also greater than 0. When we talk about the negative deviation from Raoult's law, so delta V mixing is less than 0, and delta H mixing is also less than 0. So this is actually this is cooling. This is actually cooling over here, and this is actually the heating, or we talk about like it is forming a heat, so it is heating. Now if we talk about like P total, so P total here it equals to P naught A into X A plus P naught B into X B, and P A equals to P naught A into X A, and P B equals to P naught B into X B. So here like if we talk about A and B, that is greater than the force of attraction between A B, and that is A and B, that is less than the force of attraction of AB, and PA that is equals to greater than P naught A into X A, and PB is greater than P naught B into X B, and PA is less than P naught A into X A, and here P partial pressure of B is less than P naught B into XB. Now here if we talk about like what actually the non-ideal solution. So when we mix the two container, when we have the solution like A here and B here, and we are mixing with A to B, so the changes that we are observing here, it is delta V mixing is equals to 0, delta H mixing is equals to 0. When we talk about like negative deviation, here delta V mixing is greater than 0, here delta V mix is less than 0. What actually it does mean, here if we are pouring the solution A and B together, so when we are pouring the solution A and B, and when we talk about delta V mixing is 0, so delta V mixing is greater than 0. So when delta V mixing is greater than 0, it is actually forming the bubbles, the more pressure over here. So it is more pressure over here, or when it is like A and B over here, when we mix A and B over here, so A and B like when we mix, so here delta mixing V is less than 0, here delta mixing H is less than 0. So like here it is cooling, here it is heating, it shows the positive deviation. In positive deviation, delta V mixing greater than 0, delta H mixing is greater than 0. In negative deviation, delta V mixing is greater than less than 0, delta H mixing is less than 0. So it is cooling and it is heating. So now here it is like if we talk about the examples of here, so the examples like here methane C6 H5 plus C6 H5 CH3. Here this is the example. Here the example is N-hexane plus n heptane. So there they do not have any interaction, so it always follows the round. So it is CCl4 plus it is SiCl4. And then when we talk about the negative deviation, in negative deviation we have like C2H5OH plus H2O. Here it is like a CH3OH plus H2O. And here the negative deviation we talk about, it is like HCl plus H2O, and here it is HNO3 plus H2O, and here it is like CH3COCH3 plus CHCl3. It is like Cl and Cl over here, and when H, it is directly bounded with oxygen over here, and CH3 and CH3. So oxygen and hydrogen, there is a hydrogen bonding. So due to hydrogen bonding, the final volume is contracting. So the example we have seen above, that the final volume we are getting, it is less than the initial total summation. Okay, so delta V mixing greater than delta H mixing also less than 0. And here also so the example here we have seen here, delta V mixing is 0 and delta H mixing is 0. So it is a cooling and it is a heating during the formation of the solution. Now if we talk about their curves, like what could be the curves over here. So initially we have seen the Raoult's law. So if we see all these curves, this we see the general Raoult's law, where this is like this is the P naught A, and it is a P naught B. It is like P B, here it is a P A, and it is x A equals to 1 and it is x B equals to 1. But if we see this curve, like when we mix A and B together, so when we are mixing A and B together, their repulsion force, so vapor pressure generating will be more. So here it is that is actually P naught B, it is actually P naught A. So P naught A, P naught B, so this is the curve of P total. So P total is more and here P total is less. So it is also P naught A, it is also P naught B, so it is less. So like there are there are some common properties which we observed, like here delta mixing in G is less than 0, here also delta mixing in G less than 0, here also delta mixing in G less than 0. So means it is a spontaneous process. Obviously when we are mixing two gases, two liquids, so it is a spontaneous process. And also like delta mixing S is greater than 0, delta mixing S is greater than 0, or delta mixing S is greater than 0. So delta mixing S is greater than 0, and this is like this is how we divide these categories. Okay, in all these cases, delta G mixing less than 0 and delta mixing S is greater than 0. So now we define what is the azeotropes. Okay, so azeotropes, it is a liquid mixture of two different liquids with different boiling point, which boils at constant temperature without undergoing any change in composition. Means like if we first we define there are two types of boiling point azeotrope, maximum boiling point azeotrope, minimum boiling point azeotrope. But what actually azeotropes are? So when we look like when we have a solution, like we have a solution A and B over here. So like A has the boiling point of 575 Kelvin and B has a boiling point of like 600 Kelvin, and we give the heat of the solution till the 575 Kelvin. So when we give the solution heat, so this will evaporize and we can separate the A from B. All A will come outside and it will we can separate that that in the different container. That is actually known as the fractional distillation. Now in fractional distillation, it is like mandatory, like XA, whatever we have XA, that is always equals to YA, and XB equals to YB. So X equals to YA means mole fraction in liquid, okay, liquid phase is equals to the mole fraction in vapor phase. Okay, so whatever we have the mole fraction in liquid phase, that will be the same mole fraction in the vapor phase, and whatever we have the mole fraction in of B in liquid phase, that is equals to the mole fraction of B in vapor phase. They are not equal actually when we are going through the fractional distillation. So like if we see, like when we boil at 575, all the x, like x a and y a, that is totally different. Y is more right now, but x is very less. But when we talk about the azeotopes, so azeotopes are the solution. So azeotopes are the solution of a liquid mixture of two different liquid which differ in boiling point but boils at a constant temperature without undergoing any change. Now if we talk about, we have a liquid, like a liquid which has the boiling point, like which has the mole fraction x over here, and if it has the same mole fraction y over here, and like we have a different liquid which have mole fraction like xb over here, and which is same as the mole fraction of yb over here, means it is a fixed ratio, okay, fixed mole ratio. Actually these solutions are fixed mole ratio, okay, when they are liquid. So it can't be separated, it can't be separated from fractional distillation. So from fractional distillation it can't be separate, so that type of solution are known as azeotrope solution. So that azeotrope solution, actually we have categorized earlier, it has two types: maximum boiling point azeotropes and minimum boiling point azeotropes. So now these two types of solution we have. So these solution are having a fixed ratio in liquid and vapor form, and they cannot be separated with the help of like a fractional or distillation. Now if we look further, like if we talk about the azeotopes over here, so azeotopes, if we talk about like positive deviation or maximum boiling point, so here if we talk about positive deviation or maximum boiling point, so from positive deviation from Raoult's law, or we talk about like minimum boiling point azeotopes. So here vapor pressure of solution is greater than vapor pressure of A, pure A, and vapor pressure of pure B. Now when we talk about like positive deviation, if we draw these curves, so here if we look like if we talk about minimum boiling point azeotrope, so example, if we see what is the minimum boiling point azeotrope, let's say it is 95% ethyl alcohol, so it is example here 95% C2H5OH. So what actually it is, so when we mix like A and B, so it is showing positive deviation from Raoult's law. So let's say this is the composition where it is forming 95% C2H5OH and 5% like H2O. So it is 95%. If we convert in mole fraction, so we will get this point, and get at this point there will be like if we draw the curve between pressure and temperature, so pressure is the maximum over here and temperature is the minimum over here. So here we will be getting the azeotrope, okay, this point is called the azeotrope. So at this it will be having the minimum boiling point, so boiling point is minimum over here, so minimum boiling point, and like here like x C2H5OH is here 1, here XH2O is 0, and here XC2H5OH is 0 and XH2O is 1. So this is how we divide like XC2H5OH XH2O, and it is minimum boiling point. Okay, now when we talk about this is the like so here when the pressure is maximum, so boiling point will be minimum. So as we know, then the total pressure is maximum. So when the total pressure is maximum, suppose here the pressure is like 0.8 atm at that particular time, so we need to provide very less energy to convert that into from 0.8 to 0.1 atm according to whatever we have the boiling point definition. Then what is actually boiling point? When the partial pressure becomes equal to the atmospheric pressure. So when the total pressure is become equal to the atmospheric pressure, so when the total pressure is maximum, the boiling point will be minimum, and the boiling point will be minimum, so total pressure will be maximum. So like if you see the other example of like maximum boiling point azeotrope, so in maximum boiling point azeotrope, like vapor pressure of solution is less than vapor pressure of pure A or and vapor pressure of pure B. So that's how we define the vapor pressure of solution. And we talk about like boiling point of solution. Boiling point of solution is greater than boiling point of pure A and boiling point of pure B. So that's how when vapor pressure is minimum, so then boiling point will be maximum. So this is the curve between pressure and temperature. Like if we have a solution, in that solution if we have an azeotrope, means XA equals to YA or and XB equals to YB. In that particular azeotrope, the pressure will be minimum. So here that time pressure will be minimum and the boiling point will be maximum. So this is like in here the example like 68% HNO3. In the 68% HNO3 we get like if we calculate about this mole fraction, so X HNO3 will be here or X like H2 will be over here. So in that case X HNO3 will be Y HNO3 and X H2 will be Y H2. So this is the like the curve of azeotrope. At this azeotrope we will be getting the maximum temperature. So again this is the negative deviation minimum the maximum boiling point azeotrope. So that's how we define the azeotrope. Again, azeotrope are the solution of a liquid mixture of two different liquid which differ in boiling point and which boils at constant temperature. So they will start boiling at the constant temperature, the type of solution. Like here whatever the mole fraction of XA, the mole fraction of same YA will be there, mole fraction of XB will be over the mole fraction of YB over here. So they at the temperature they can be separated through the fractional distillation. So these are the points. That's how we calculate the azeotropes, and that's how we see the deviation from ideality of the solution and ideal solution, non-ideal solution, and azeotropes.